For years, you have been told that you cannot take the square root of a negative number. In this unit, we shatter that limitation entirely. Complex numbers represent one of the most profound expansions of the number system you will encounter in your A-level studies. By introducing the imaginary unit, we unlock an entirely new two-dimensional plane of mathematics. This allows us to solve polynomial equations that previously had no real solutions, bridging the gap between algebra and geometry.
We start by defining the imaginary unit I, where I squared equals -1. This is the single spark that ignites the entire topic. This single definition creates complex numbers in the form a plus bi. You will master the basic arithmetic, adding, subtracting, multiplying, and dividing these new numbers, just like normal algebra. The only new rule is replacing I squared with -1 whenever it appears in your working.
To divide complex numbers, you need a powerful new tool, the complex conjugate. By flipping the sign of the imaginary part, you can rationalize denominators and clear fractions effortlessly. Crucially for the Paper 3 exam, if a polynomial has real coefficients, any complex roots will always appear as a conjugate pair. Examiners expect you to state and use this vital property without prompting to find missing roots.
Once the algebra is secure, we map these numbers onto a two-dimensional grid called the Argand diagram. This geometric shift changes everything. A complex number becomes a coordinate or a position vector. Its distance from the origin is its modulus, and the angle it makes with the positive real axis is its principal argument. Always sketch this diagram to ensure your calculator gives you the argument in the correct quadrant.
Modulus and argument naturally lead to the polar form of a complex number, which is essential for advanced operations. Instead of Cartesian coordinates, we define the number by its size, r, and its direction, theta. Why do we need this? Because multiplying and dividing in polar form is incredibly fast. To multiply, you simply multiply the moduli and add the arguments. It transforms complex algebraic expansion into elegant geometric scaling and rotation.
Finally, we use all these tools to describe geometric paths or loci in the complex plane. You will learn to translate complex equations into circles, perpendicular bisectors, and half-lines. For example, an equation setting a constant distance from a fixed point is simply a circle. The hardest exam questions will ask you to find the maximum or minimum modulus on these loci. The A-star candidate recognizes these as geometric puzzles, solving them with an accurate, large sketch rather than attempting messy algebraic substitutions.
To master this unit, you must nail the basic arithmetic, memorize the polar multiplication rules, and always think geometrically when dealing with loci. You are now ready to begin the mathematical journey into the complex plane, starting with the formal definition of the imaginary unit and the square roots of negative numbers.